In this video, we're going to look at some of the history behind science's search for the fundamental building blocks of what it is that makes up matter. In this video, we'll look at things such as atoms and our current understanding of how they exist. We'll also look at the periodic table, and in the periodic table, we'll look at the atomic number of elements, how the periodic table is organized into groups and periods. We'll look at a special subset of the periodic table known as the noble gases, and we'll also do a brief introduction of metals, nonmetals, and metalloids. The idea that all matter is made up of small, discrete units of stuff has been around since ancient Greek and Indian philosophers first started pondering these ideas. However, our modern understanding of atoms has only really come into being in the last 100 years. I've included this quote by the Greek philosopher Democritus because I think it best sums up how the ancients thought about atoms. The last line, "but in reality there are atoms in space," is actually incredibly close to the truth. However, being in a time 400 years before the birth of Christ, this was a very advanced idea, and at the time it was closely linked to theology and philosophy as opposed to experimental science. So based upon our current understanding, an atom is the smallest particle of a chemical element that can exist. This is not to say that it's the smallest particle of matter, but rather that it's the smallest particle of matter that can still be identified as belonging to a specific chemical element. This can be seen here. An atom consists of a nucleus at the center, surrounded by a cloud of one or more electrons. The nucleus itself is made up of protons and neutrons, protons being positively charged particles, and neutrons being particles that have no charge. The negatively charged electrons circle around the nucleus at quite a distance. This is a slightly different diagram showing exactly the same thing. In the middle, you have a nucleus made up of positively charged protons and neutrons which have no electrical charge, surrounded by a cloud of electrons. Relatively speaking, there is a huge distance between the nucleus and the electrons. Hence, most of an atom is made up of empty space. The periodic table as we currently know it really came into being during the 19th century. Dmitri Mendeleev is credited with being the first person to organize all of the known elements at the time into some kind of structure. If you have a look at the diagram here, this actually looks like the periodic table turned on its side. You can see H for hydrogen, Li for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc., etc. There are, however, some elements missing from Mendeleev's table, and in fact there's a number of inaccuracies in his table. However, this was the first starting point, I suppose, for a concise and logical organization of the elements. The first attempts at constructing a periodic table listed atoms in order of their atomic weight. Each atom was thus given an atomic number. In 1911, Ernest Rutherford, Niels Bohr, and Antonius van der Broek suggested that this could be improved by ordering them based upon the charge of their nucleus. In 1920, Rutherford discovered protons, which were shown to match exactly with the atomic number. Thus, the symbol for atomic number, Z, comes from the German word Atomzahl, meaning atomic number. From the work of Rutherford, we now know that the atomic number of an element matches the number of protons within the nucleus of that element. The convention for labeling the atomic number is as follows. Around this red box here, you'll see the X represents the chemical symbol for the element. The atomic number, which is the number of protons in a nucleus as discovered by Rutherford, is termed by the letter Z. The letter A equals the mass number. This is the number of nucleons in a nucleus, that being the number of protons plus the number of neutrons. For example, looking at lithium over here, it has an atomic number of 3, it has 3 protons, but an atomic mass of 7, meaning it has 3 protons and 4 neutrons. The modern rendering of the periodic table has rows, called periods, and columns, called groups, and each of these have specific characteristics. Elements in the same group or column share similar chemical characteristics. Elements in the same period, or row, have the same number of orbitals, which are layers of electrons circling the nucleus. One of the biggest things missing from Dmitry Mendelev's original periodic table was a group of happy elements in group 18. These gases, known as the noble gases, have full outer shells of electrons, so they are not chemically reactive. We say that they are inert. Helium, the first of the noble gases, has 2 electrons in its outer shell. Neon, the second noble gas, has 8. Both of these gases are inert gases. They don't react easily, or if at all, chemically with other elements. If we now look at the periodic table in its entirety, you can see that color-coded on this picture shows the 3 different areas. We've got the yellow area, by far the largest part of the periodic table, which is known as the metals. These are elements that have particular characteristics. There's also the non-metals, shown here in blue, and straddling the two is a green area, which are known as the metalloids. In our next video, we'll look at these areas more specifically and explain some of the characteristics that make up metals, metalloids, and non-metals. Before finishing this video, let's recap quickly. An atom is the smallest particle of a chemical element that can exist. Atoms consist of a nucleus at the center, surrounded by a cloud of 1 or more negatively charged electrons. The empty space between the nucleus and the electron clouds makes up most of the atom. The nucleus itself is made up of positively charged protons and neutrons which have no charge.